Okay, thank you, Charlie. And I will now continue with the an overview of the main results we had in TraceBot, which is this presentation. Yes, so Charlie already mentioned it a bit, but I will insist. I mean, what I will present, it's a result of a joint work of a consortium. So we were in TraceBot, a European project, Research and Innovation Action, and the consortium was composed of the following entities: Biolago with Michael Newman, that unfortunately could not join today, coordinating the activity and provided access to their network. Charlie, that just talked, that helped us to describe the use case, characterize the use case, and also get in touch with the regulation bodies. Aztec project that could not join us today, that helped us to generate the demonstrator that we'll see later on. The University of Bremen with Franklin Kangago, that is, I think, connected, and that we'll talk to this afternoon about the reasoning framework they put in place for TraceBot. Markus will later present their activity on the perception that they provided to the consortium. And then CEA provided their expertise on healthcare robotics, and Mathieu will present the work done on the dexterous gripper. And Tecnalia was also involved in different development related, of course, in robotics. And with that consortium, we started directly with a clear use case that you, I guess, probably all know, that is the sterility testing. So membrane-based of sterility of liquids. So it's a very critical process that must be conducted for validating any liquids prepared in pharmaceutical medical domain. But as you can see, it's still a manual process. And we thought that it was an interesting use case to look at, to showcase what we can do with advanced robotics, to showcase the capability of robotic system nowadays in terms of perception, manipulation, verification, traceability, and so on. And of course, this concrete example provided us a set of scientific and technical challenges that we were also pleased to look at. But globally speaking, what we wanted to see is how we can bring an agile robotic concept towards the pharmaceutical domain. And with this, what we don't want to do is to propose a totally automated solution in which every motion of the robotic system will be pre-coded, assuming that all items will be a predefined position inside the environment. We wanted to have a bit of flexibility so that the system can adapt to different variability in the environment, to small changes in the environment, but still be able to conduct the activity. Also, introducing agile robotic concept normally facilitates the programming of the system. If we want to make a complete automation, we need expert in programming this type of devices. But if we have an intelligent robot, then the configuration of this system should be simplified. But of course, to get an intelligent robot, we need to embed intelligence inside the robotic system. And in that context, we have identified a set of, I would say, functionalities, capabilities that needed to be associated with the robotic platform, and that we have been working on during this period. And these functionalities are capability of perception, dexterity, control, learning, tracing and verifying, and reasoning. I will briefly comment all this item, and then the technical session will permit to extend most of this discussion point. So in terms of perception, the objective is to be able to localize, detect, and estimate the pose of the different items that we want to manipulate. The problem is that most of the items are transparent, so that it's quite difficult to see where they are in the environment. And even if we use advanced camera, 3D camera, well, even in the 3D image, it's not that obvious to see where it is because it's transparent, right? But our colleagues of WIEN with Markus have been proposing deep learning techniques that takes into account some physics-related features, such as how the light goes through transparent object, to create a model that enables to handle this type of situation. And we have been testing it and compared to the state of the art. So believe me, on the left image here, we have some transparent object that we barely don't see with our eyes. And we could demonstrate that our techniques of detection enable to detect and estimate the pose in a way that is well beyond the state of the art associated to that operation. And we have been testing it in different situations, different type of objects, and we were always able to detect this transparent object with the approach that have been developed, and that will present Markus later on. So altogether, we are able to detect the different items we want to manipulate, being the bottles, the canister, but also with other type of deep learning pose estimation to detect some complex objects such as the needle that we are going to manipulate during the process. So we can perceive the object. We want to manipulate them, to grasp them, and to manipulate this item. So how do we do that? And that's where Mathieu and Sia has been working intensively during the project for designing a dexterous gripper that you see on the lower right. So it's a gripper composed of 4 modular fingers with tactile sensing embedding in each of the palm of each finger. And the design of this gripper has been really made looking at the use case, looking at the grasping patterns used by the human, the way the human manipulate the different objects, the forces, interaction forces that have been observed, and all that information enabled to define the appropriate structure of this gripper that has been tested and validated to showcase that we can manipulate the different items, such as the bottle here, the canister, the clamp that should now move here. And also on the red cap here, you can see that the trace that we have in the tactile sensing, so that we can detect the contact with the object, and we can use that information to verify whether we have been grasping an object correctly, and also combine that information with vision to improve the estimation of the pose of objects that are held by the gripper. So with this different example, just to showcase the capability of the gripper, but I'm pretty sure Mathieu has plenty of other videos to show you right after. But the message is that we are able to manipulate the different items that are present in the use case that we have been looking at. So we can detect, we can manipulate. Now we have to move the robot, right, from one side to the other. And that's where the control functionality comes into the picture. So at Tecnalia, we have been working at different level, and I will detail that later on in the technical session. But at the highest level, we have been proposing to use a skill framework in which each of the capability of the robot, including perception, grasping, and so on, are encoded as a skill, as a functionality that is provided by the robot to perform a given task. And then at the lowest level, we have been also working on specific controllers that enables to perform the different manipulation that we are interested in. We will see later on the canister insertion, the needle manipulation as well, that has been implemented with this low-level controller. And we could also handle the joint control, synchronous control of multiple arms, as you have seen in the video bottom right, in which in the first stage, well, the 2 arms are used sequentially to prepare the system for making the tube insertion, but during the tube insertion that will start soon, then the 2 arms are controlled within the single control loop jointly to make sure that we maintain a certain tension into the cable, and we correctly insert it into the holder, as you can see there. So we have a bunch of controllers and a bunch of skills that are available to program the robotic system. And so the next functionality that is required is to be able to teach the robot or to make it learn some specific actions. And we have been with CA and the University of Bremen looking at different directions, different ways to perform this activity. The first one that is, I would say, the most classical one is to use a graphical interface so that the operator can select the different skills he wants to use to create the program, the process the robot should perform. Another option that I will also present later is to use a kinesthetic teaching so that the operator move directly the robot system around to show to the robot which object, how to manipulate them. And in the meantime, the robot learns, recognize the action that are used and reproduce it on its own later on. We can also use a demonstration to teach to the system new manipulations. So I will show you a video later on about how we can use that to augment the number of skills provided with the system. And in a more prospective way, our colleagues of Bremen have been working on trying to identify directly from a visual flow the primitive skills that are presented in the video, are taking advantage of course, deep learning techniques to recognize the actions, and also an ontological representation of the environment to encode the extracted information, bring it to a virtual avatar as you see in this image, but also possibly bring it to a robotic platform later on. So most of these items I will detail that in the following section. Another aspect that is of course important in TraceBot has been the tracing and the verification layers, because keeping traces and verifying the action is key for the domain we are interested in here. And one of the components we have been using for that is the traceable semantic twin developed by Bremen. In which we have a simulation of the environment that represents the two robotic arms, the different items, objects that we are going to manipulate, and that mimic the real world as the robot moves in reality. And it's not just a visualization, it's really a simulation that takes into account the interaction forces of the object, the physics of interaction of the different items, so that we can not only use it to reproduce what has been done, but use it also to verify whether what's taking place makes sense physics-wise. And that's where we can take first information for verifying the operation. For example, we can deduce from the data provided by the simulation that the canister should not be inside its tray, because given the current pose of the system, it should fall, as you can see in that video. So we can extract that information from the simulator. We can use the simulator as well to check possible motion and detect that some motion are not feasible, because in that case, the canister is entering into contact with the pump, for instance. And we can also use it to make some imagistic reasoning, as you can see here, where we can assume that once we insert the red cap onto the canister, then the visual perception should be corresponding to that digital image. And we can compare the real image on the left with the digital one to make sure that indeed there is sufficiently overlap so that it seems that this insertion has been correctly performed. So the simulation can be a first source of verification. But we have been also working on other modalities for the verification, such as using different modalities to refine and improve the pose estimation, like taking into account the fact that the object is lying onto a plane, so that we can refine this way the pose that has been initially estimated by the pose estimator. We use tactile information to verify whether grasping is correct according to what have been learned previously, so that we can define whether this clamp closure is satisfactory or not. And we can use also kind of odometry information, because we are manipulating a canister. From the ontological representation of the environment, we know the width of this, or the diameter of this canister, so we can verify whether the aperture of the gripper is coherent with the estimated diameter of this item. So we have here a set of verification means that we are combining thanks to the reasoning framework developed by Bremen. And this reasoning framework relies on first an ontological description of the environment that describe the characteristic of the different item of the scene, but also covers the action of the robotic system, so that we also describe for each of the skills or action what are their precondition and how they impact the environment once executed. And with all that information, we can perform, as already mentioned by Charly, functional verification. Given the current state of the system as understood by the reasoning system, given a task that we want to perform or an action or skill, we can first verify whether the condition for executing that action are satisfied. So can we launch this operation? That is, if I want to grasp an object, is the gripper free of object, for instance? If yes, then we can execute the operation, and automatically, depending on the impact of that action on the environment, we can deduce which is the proper verification means to use to verify and to confirm that the operation took place correctly. And all this is enabled thanks to the reasoning framework provided by Bremen, and Franklin will detail that, I guess, later on today. And another aspect of the reasoning system is that all the data collected is used to create a memory, an episodic memory, a so-called narrative-enabled episodic memories that provide a complete description, a comprehensive description of the action conducted by the robotic system that enables, on one side, to comment and to describe the activity in terms of high-level actions. So what are the main operations conducted by the system? And for each of these different steps, to give access, if needed, to a collection of sensor data or pose estimation of objects and so on, and robot configuration that can be used to put us back again during the execution, and also understand when it is appropriate why a given action did not succeed as expected. And all that information is then combined inside the audit trail that we generate. And as you can see in this screenshot, and I will detail a bit more that in a few minutes. And in this audit trail, we combine semantic information about the different actions that took place, together with some means of verification that provide some indication on how the system validated the operation that took place, and that can be used to, when needed, to understand if there was an issue with the execution, what was the issue encountered and how we identify it. But otherwise, if we are happy with the execution and the system say it's successful, then that's done. Yeah. So I think that with this, I provided a broad, too quick overview of the different main, I will say, contribution that we had during the execution of the project in different direction, in terms of manipulation of object, perception, robot control, the tracing verification, the reasoning. We also looked at the programming interface, programming by demonstration, and all this combined together to be able to generate at the end an audit trail that provide a trace of good execution of the process, and with traces of verifications that have been employed automatically triggered by the system itself to verify the good execution of the process. Of course, I mean, we think on one side that most of the concept that we have been developing here could be applied to other type of processes. We don't think that the perception layers, the control layers are so specific to the sterility testing process. So we do believe that some of this development could be applied to other processes and other environment. And there are still some research to conduct. There are still some challenging steps to handle, in particular manipulating very small objects or deformable objects. And in that case, it could be interesting, for example, to switch from a static camera that we have here toward a high in-hand configuration having a camera nearby the gripper so that we can more precisely see small objects while we get closer to them. And also, of course, another interesting activity will be to bring this proof of concept toward a first complete prototype with the robustness required. But altogether, it's already a good illustration of capability. And with that, I'm closing this overview.